let's try to go on and go on with today's topic and today's webinar. I'm very pleased to welcome Dr. Alessandro Dosio. He is a senior scientific officer at the European Commission Joint Research Center, and which is responsible for regional climate change modeling. Dr. Dosio holds a degree in physics from the University of Milan and a PhD from Wageningen universities. And his work involves the production, the evaluation, and the analysis of the climate change projections, both at a regional scale, so to assess impacts on various sectors. He has very many achievements along his career. Let me just point out that he was the lead author of the chapter about linking global to regional climate change of the sixth assessment report of the Intergovernmental Panel on Climate Change of the United Nations. But he is also recognized on the Reuters hot list of the world's most influential scientists, climate scientists. And also the Stanford University has listed him among the world's top 2% scientists since 2022. And the topic of his lecture today is global warming, so the physical science basis, understanding what has happened and what we can expect. Quite evidently, this is a subject on which he is extremely knowledgeable. So I am very grateful and honored that he was able to accept our invitation. And we all are very much looking forward to listening to him and asking him some questions. You can use the chat to ask your question. And at the end, we will have a quick and short question and answer session. So thank you so much, Dr. Dosio, for being with us today. And the floor is yours.
Okay, thank you for the invitation. I hope you can hear me well. It's actually a pleasure to be here. I'm very happy usually to speak to students where you're not students anymore, but you're actually the one that actually talk to students, and the young generation, who is the generation that have to fix the mess we've made, basically. So let me share my screen. So I can do that. Yeah, share. Okay. And now you should see my, okay, you should see my presentation, I guess.
Perfectly.
Okay. Yeah, so I thought that when we discussed what I should have said to you, I said, well, I think it would be a good idea to start with some basic concepts about climate, because there is some confusion even after 30 years. The science is saying the same stuff, but still something is not always very clear. And basically, I will start with the preamble, and the preamble is: do you see what I see? Or with our goldfish. And I say goldfish because goldfish are notoriously short memory. Even someone says that's not true. And well, I think that we humans all as well have a short memory term, as we'll see later. So, well, we know it's hot. Okay, everybody say, well, it's hot, summer is hot. This year was extremely hot. Last year was really hot. Well, is it? And you know about the legendary figure of the grumpy old man. The grumpy old man is basically a middle-aged man, can be me. I was born in the 70s, so I'm in my 50s. I have two kids. We are in their 20s. And these people sometimes come up with this kind of sentences. I remember it was very hot when I was young. Okay. Oh, it was too hot when I was young many years ago. Or something like, of course, it's hot, it's summer. You don't expect to build a snowman in summer, you know. Or something like, oh, this year or last year, whatever, was particularly cold, particularly rainy, particularly snowy, whatever. Or a sort of variation of the same stuff, which is where I live, or where my sister live, or where my cousin-in-law live. The weather was actually very cold, very snowy, very windy, very not hot at all. So where is this climate change? This is the question of the old grumpy old man. Well, believe me, I wrote that page before I read this one. This one is an Italian blog of a journalist from an Italian newspaper. And these kind of pages are actually read by thousands of people in Italy. So it's in Italian, but I will translate it for you on the go. So the first sentence says, oh, always in cyclic in the climate. Of course, there have been always periods when it was very hot or very cold. And when I was young, it was very hot in the summer. I remember that my mom told me to stay at home. But these also, they're always cyclics, and every some years it's hot, and then it's cold, and then so. And what about June? Of course, June is very hot and dry. But if you go to the south, it's hot and dry. If you go to the north, actually, we had been raining a lot this year. But about this, I would like to just remind you that, okay, this is a picture of the eastern part of Sicily. This one, you can see my pointer. This is the Mount Etna. And this picture were taken in January 2023, so last year. And this picture were taken in 2024, so 1 year later. And Sicily hasn't seen a single drop of rain in 1 year. It's one of the biggest drought in the last at least 20 years. Just to put some things into context. Well, of course, it's hot. It's summer. This is my favorite sentence. And here we go. Nothing has changed. So where is this climate change? So this is a blog that was posted in the 21st of July, 2024. So yesterday, basically, okay? So there is some people still that think that nothing has changed, that is not hot at all, or why are we complaining, basically? So let's put some basic concept about climate, about the difference between climate and weather, natural variability, extreme events, and so on. And this is something that I think for you it's important, because when you talk to students, it's important that you have the idea clear. And then I will actually tell you 3 things in this webinar. The first thing is some basic concept. Then we will go through what has happened in the past. And then we have a little view of what we think may happen in the future. And then we'll end with some personal, let's say, statement or personal idea. And this is what I said to students when I went to school and I talked to students. So I think this some thing that maybe you can borrow if you actually talk to students and about these problems. So the first thing is weather and climate. Now, I don't know where you live, but in Italy, we have usually, or we used to have, what is called a 4-season wardrobe. A 4-season wardrobe is a big wardrobe when you actually store all your clothes for a certain season. For instance, in winter, you have your section, you open your doors, and you have all your warmer clothes there. So the climate is basically this section of the wardrobe, the clothes that you are expected to wear. Okay, you expected to wear winter clothes because it's winter. Then there is the weather. That's actually the choice that you make every day, because one day, for instance, can be very hot, so you don't need your jumper, or it can be very cold, so you need gloves and scarves. So this is the difference. The climate is the weather that is expected on long term, on average, let's see, and the weather is the day-by-day variation. A bit more technical, let's say. Let's see what actually influences the climate. Well, the climate is actually very complex, and everything starts with the sun. The sun is our basic source of energy for everything on Earth. Then, of course, there is the clouds, the atmosphere, the land, how the land changes or how the land is used by humans and so on. The ocean, the water, which is a major impact on the climate, and the ice also. And then there is the volcans. I will talk about volcans later on. And then at the end, there is the human component. Then the problem is that all these components don't act by themselves. Of course, they act by themselves, but they also interact amongst each other. And to explain this, I make you an example, and I did 2 things: a white car and black car and the sun. And I sure that everybody understand or experience what happens when you park your car under the sun in summer in Italy, for instance, and the difference between a white car and a black car. The white car is cooler. And there is a reason for that. The reason is called albedo. The albedo is the fraction of solar radiation which is reflected. And the white surface reflects much more light compared to the black one. So the white keeps the temperature lower compared to the black one, or compared to dark surfaces. And then there is some ice. And what has it to do with the climate? Well, this is the problem, one of the problems, which is called a positive feedback between the albedo and the sea ice. Assuming you have the sea, which is covered by ice, for instance, in the North Pole, and this ice, since it's white, actually keep the temperature low because it reflects all the light, mostly of the radiations. Okay, so the albedo is very high. Now imagine you raise the temperature, the ice start to melt. And under the ice, there is water. Water is darker. So water actually absorbs more energy and enhance the temperature, actually warms the climate. Warming the climate, it means that more ice is melted. And so this is a circle, a dog that is its own tail. This is called a positive feedback. Another big positive feedback is the one of the nitrogen in the permafrost. Permafrost is actually land which is permanently iced, and the nitrogen is very, very powerful greenhouse. So the nitrogen is actually stored there; it cannot escape. What happens? The temperature rises, the ice start to melt, and nitrogen is actually released in the atmosphere, and this creates more greenhouse gases. So more greenhouse gas effect, and so more heat, and then more ice is melting, and so on and so forth. And this is one of the biggest problem we will have, is actually the permafrost in the, especially for instance in the northern latitude, will melt. Now I have to tell you something about natural variability, which is a very important concept when we talk about climate and climate change. You see that climate varies a lot, the weather climates a lot, changes a lot. And assuming you have the temperature, you measure the temperature of where you live every day. So the temperature goes up and down. Of course, during the nighttime it's very low, and during the day it's very high. So you have this kind of cycle day by day, the daily cycle of temperature. Then you have, of course, another cycle, which is overimposed to that, which is the seasonal cycle. For instance, from June, then July, the temperature is higher, and then it goes back again. And still you have this up and down because of the daily cycle. Then you have the yearly cycle, and then you can even have multi-yearly cycle. And these are usually driven by ocean mode, like the Nino, for instance. Okay, this can be like 10-year cycles above all of this. And as end up result, you have that the temperature of the Earth, let's say, in years varies a lot. You have up and down. It's not really, there is nothing really constant. You see, up and down, up and down, up and down. Now, there is another component that is very important. I actually told you before, and this is an example. This is the anomaly of temperature. So actually, it's the temperature relative to the mean in Europe in a particular year. This was 1816, summer 1816. Now, I would like really to ask you if you remember what happened in 1816. Actually, we have to go back 1 year. It's actually 1815. In 1815, in April 1815, there was a big volcano in Indonesia. It's called the Tambora. And this was the biggest explosion in human history. The volcano actually erupted for months, and the burst into the atmosphere, actually first, into the atmosphere, a lot of ashes. And so much that actually the sea around the island was covered of a thick layer of ashes, but not all of that. Most of it went into the atmosphere and then went in the tropospheres, and then actually covered all the globe. And since these aerosols basically have a property of actually reflect the solar radiation, this has a very cooling effect on the temperature of the Earth. The Earth actually that year was 3 degrees lower, the temperature of the mean global temperature in the entire Earth. And even this year after that, over Europe, the temperature was still 3 degrees below. And this year was called the year without summer. It was snowing in actually northern America in July, and you can imagine the disruption of, for instance, agriculture. It was really a disaster. So this is just to tell you that temperature can go up and down for many reasons, and these are all natural reasons. So this is why it's called natural variability. The problem is that in the last, let's say, 50, 60 years, we had something which is different. We have this trend, increasing temperature, mean temperature, and the measure said that in the 2023, now 2024 can be even a bit higher than that. The mean temperature was 1.2 degree higher than the mean, let's say the pre-industrial mean, the mean between the 1850 and the 1815 and 1900. It's not only that. We have seen that every decades in the last 50 or 60 years was warmer than the preceding one. And this increase, this rate of warming is unprecedented in at least the last 1,000 years. And the last decade was warmer than any multi-century average in the last 125,000 years. Okay, so there's something peculiar. Now, there is another important concept that you have to understand is that the climate and the variation of the climate really depends where you live. Not everywhere in the globe warms in the same rate. For instance, the northern latitude warms faster. One of the reasons because this happens is because the land actually warms faster than the sea. And the northern latitude has a higher percentage of land compared to the southern hemisphere. So this is one of the reasons why the northern latitude warm faster. But then also the importance for natural variability compared to the changing climate is important, depends where you live. Assuming you live at the tropics where temperature doesn't really change a lot during the year. So you have this variation is nearly very the same. And this orange, let's say, band is what we call the natural variability. I mean, what we expect in terms of change of the temperature. And then you have this change, okay? So if this change is even comparatively low, but since the natural variability is so low, if you make the ratio between the change and the natural variability, you can have this ratio, which is called signal to noise, very higher, much higher than 1. Whereas you live in Europe we have the temperature varies a lot. And so the natural variability is very high. So the rate between the change and natural variability is not so big. It means that this change can still be considered natural because it can still fall into natural variability. So this is why sometimes it's not easy to attribute, that's the term we use, the change to, for instance, human influence, because it still can be natural, still can be due to natural variability. One of the problems is that even over Europe, where we have seen that natural variability is so high, there are some components, for instance, some statistics for the heat waves that have statistically changed in the last 30 years. It means that one generation, from my generation to my children's generation, only 30 years, was enough for these characteristics to change. And when I say that it's enough, it means that the mean state of this, for instance, the heat wave number, in the period between 1991 and 2020 is statistically different than the same statistic in the period 1961, 1990, okay? And not only that, but there are some people, if you look at the next 20 or 30 years, whatever, let's say the generation of my grandchildren, if I will have grandchildren, they will live in conditions that not only are unfamiliar, means that this signal to noise ratio is higher than 1. There will be some people living in a condition where this signal to noise ratio is higher than 2. And this means 2 standard deviation. To put this in context, if you live, having something that's higher than 2 standard deviation means that in a normal climate, this condition will happen once every 40 years. Okay, so these people will live in a condition where they will expect once every 2 years, which something is called the normal state, something that usually in my time happened one every 40 years. Okay, so this basically we just said. So another extremely important concept that you have to understand is the concept of extreme event and probability. It's not difficult, so I don't show you any formula, don't worry, but it's very important that you understand, and especially you understand how we treat probability. So this is actually a very famous picture, became very famous because it's so nice. Every line is actually a measured temperature in Switzerland between 1864 and 1990. Okay, so you see, if you plot them, you will have something like that. This is the minimum temperature well measured in 1912, and this is the highest, the one measured in 1947. And if you plot, use whatever, you can plot this curve, which is actually the probability of having one of this temperature. And when you see that this is the higher point of this curve, means that this temperature around, let's say, 14.2 degrees, is the one that we expect to be the most, the one that occurs the most, because it's on the top of this probability curve. So this is the normal state, the normal, what we actually expect most probable. Then we have this is called the natural variability. So this is what this kind of temperature are the one that we expect because of natural variability. Of course, the probability is less than the most probable, but they can still happen. There is nothing wrong with that. They happen because the climate change or the weather changes, for instance. Then there is an extreme. An extreme is something that actually is, let's say, out of this shape of this curve. So it's so far that maybe it's beyond the normal, beyond what we expect, let's say 2 out of 3 times or even 4 out of 5 times. So this is what we expect, we call extreme. Something beyond the natural variability, something at the, we call at the tail of this probability distribution function. And this still is something that happened. It's not a fiction. This happened. We don't know exactly. We can see why, but this is not the problem. This is called an extreme. I will go back to this feature later on. Now, let's have a look at what has been recorded in the last, let's say, 70 years. This is the maximum global temperature. So it will go up, as you see. But the point is that the last 10 years were actually the warmest 10 years happened all in the last 10 years, as you can see. This is another picture, the same sort of message. Each of these gray line is the annual temperature, the annual cycle of temperature. This is January, July, August, December, from whatever, 1994 to 2022, okay? Then there was 2023, which is the yellow line here. You remember that 2023 was very, very warm, especially in the second part of the year, which was actually the warmest year since 1940. And then we have 2024, and this is the red line. So all temperature until, say, June was actually the highest temperature recorded from 1940. And on the 22nd of July this year, we had the highest temperature day or record in history. We had 63 countries which experienced the warmest June on record in 2024. To put this in context, in Europe, the temperature for June was 1.457 degrees above the 2020 average, not the pre-industrial, okay? So there was a huge amount of warming in Europe, in summer Europe. Last of this plot, this is the same, but this, instead of being the temperature, is the anomaly compared to pre-industrial. And you may have heard about the Paris Agreement, which the Paris Agreement was a milestone in policy agreement between the state, the countries. And the idea was to try to keep temperature at the end of the century well below 2 degrees Celsius compared to pre-industrial. And the idea was that it would be even better if we can keep it temperature below 1.5 degrees. Well, for the last 12 months, from let's say May 2023 to June 2024, the mean global temperature of the Earth was above 1.5 degrees already. We have 1 year, it was the first year, 12 months, consecutive months, where the mean temperature of Earth was already above 1.5 degrees from pre-industrial. Okay, so this is our old grumpy old man. These are his questions. I remember it was so too when I was young. Well, not really. Of course, it's called hot is called summer. No, not really that one as well. This year was very wet, cold. It doesn't really matter because we are talking about long term, not the specific year. And also, it doesn't matter where you live because climate is a global mean. It's not the specific position. Okay, so maybe our grumpy old mud give up and say, well, okay, maybe it's hotter than it used to be. Well, not really, because you can say, well, it's the sun, or it's natural variability. Or, well, actually, what we emit as atmospheric CO2 is really a tiny fraction of the global carbon cycle. Well, actually, this is true. It's true. Part of the components we know it's the sun, and part of the problem, of course, is natural variability. And also, we know that anthropogenic CO2 is a tiny fraction of the global carbon cycle. Then you can say, well, see, that's not us. It's definitely not our fault. Or, what? Who cares if it's 1 degree Celsius? Maybe it can be even better. I like warmer climate, and actually, in the northern countries, 1 degree can be even nicer. Well, we see that this is not true. Either of those sentences are not really true. Okay, how can we know that is actually our fault? This is a picture taken from the IPCC frequently asked question. And I don't want to enter into much detail, but I just point out a few things. So the black line is the measurements of temperature from 1850. And so we have this trend. Now we have models, climate models. The climate models are actually very complex, but basically they are based on physical law. And they include, of course, all the natural components. They include also the aerosol, the volcano eruption, for instance, and the human-induced, the emission from greenhouse gases. And the nice things of models, you can play with them. So you can maybe make simulation when you also only consider natural factors. And if you do that, you have this green sort of shade. So the natural factors only cannot explain the trend in temperature in the last 50, 60 years. And if you consider the natural variability, the natural causes plus the greenhouse gases, you have this red, and you actually can see that it's actually too much. And then you have to consider also the aerosol. The aerosol, as I told you, have a cooling effect. Okay, so they actually tend to cool the planet. So the combination of natural variability, greenhouse gases, and aerosol at the end matches very well the trend in temperature, observed trend in temperature, which is the gray, which is the models, and the black, which is the observed temperature. I tell you something about aerosols because in a way it can be a sort of problem. This is the technically is called sunshine radiation over land. I mean, how long the day lasts. If you want, how bright is the sky? Okay, over Europe, and this is the trend in the last 60 whatever years. And we see that in the last 30, 40 whatever years, there is a positive trend. So the sky is becoming brighter. And why is that? This is because, especially over Europe, we have the so-called air clean policy. The air quality has improved. It means that we have removed aerosol from the sky, basically. So the air quality we breathe is much better than it was 50 years ago. But removing this aerosol, we actually increased the temperature because aerosol have a cooling effect. So this is one of the problems that we have to take into account this policy when we make policy for instance, how to tackle climate change. We have to also consider that part of the problem is because it's not a problem. One of the problem is because clean air policy actually have a warming effect. Of course, we don't want to go back to the smog we had 50 years ago, but this is part of why the solution is so complex. Okay, now another way of analyzing why we know that actually it's us. This again is the drought in Sicily, the one I showed you before. And there was a study by this organization, which is called the World Weather Attribution, which I contributed. What they do is to analyze the effect of anthropogenic climate warming on a specific event. And they studied the impact of climate change on this drought in Sicily. And what they found is that this drought, which is more or less 1 in 100 year drought, maybe that naturally it will occur 1 every 100 years, the intensity of this drought would have been much lower without climate change. Not also that, but it would have been actually less probable. They say that the climate change increased the probability of such event by 50%. So this is another fingerprint, if you want, of the fact that, yes, this kind of event are, the frequency and intensity are actually influenced by anthropogenic climate change. Now, I end up with the IPCC summary for policymaker. This is the working group 1. I have some strange noise. Okay, the working group 1 summary for policymaker. So I have to put things in context. The IPCC writes what is called the assessment reports, which is more or less 2,000 pages. Maybe assess all the science in the last, let's say, whatever. So it's a very, very, very big book that nobody reads. So we make first a technical summary, which is a summary of the 2,000 pages, which is around probably 500 pages, which nobody reads. And then we make a summary of the summary, which is a 40-page, which is actually one that the government actually read. And this kind of document then enter into the negotiation, okay, international negotiations. And the first sentence that you read on this summary for policymaker is that one. It is unequivocal that human influences have warmed the atmosphere, ocean, and land. Now, there is a history behind this sentence. The history is that this sentence is not what the scientists proposed. The sentence that the scientists proposed was this one. Human influence has warmed the climate system and widespread rapid change, blah, blah, blah. So what happens? This summary for policymaker actually is approved in the plenary session of the IPCC, what it is. The plenary session is a 1-week meeting when all the government meet and the scientists that wrote the IPCC report meet, and they discuss the finding. And these sentences are approved by the plenary word by word, okay? So what happened is that the scientists proposed these sentences, then the government proposed a different version of the sentences. That is this one. It is unequivocal. So this was a sentences that was proposed by the government and was approved by all the government of the world, including, for instance, Saudi Arabia. So when you hear somebody say, what is not very clear that climate change is created by us or science is divided, that's not true. There is not such division in science, and all the government, all the world put black on white that is unequivocal that the human-induced climate change has happened. Now, this is another picture from the IPCC Summary for Policymaker. This is the, let's say, the attribution of extreme heat, actually, over all the region of the world. This is more or less the world. Okay, this is Africa, this is Europe, this is North, South America, this is Australasia. And so where you see red means that this particular index, this case is extreme heat, has increased. These are observations, okay, in the last, whatever, 30, 40 years. But not only that, if you have 3 dots, means that this is we are very confident that this is attributed to human-induced climate change. So basically for extreme heat, everywhere in the world, mostly everywhere in the world, this is being attributed to human-induced climate change. For precipitation is a bit different for many reasons, which I don't, well, we can discuss, but it's not necessary now. But still, for instance, you see that over Northern Europe, the increase in extreme precipitation still has been attributed to human-induced climate change. Not everywhere. In some countries, not possible to attribute this change. In some countries, the precipitation has not changed, like for instance, the Mediterranean. But we know, for instance, that the Mediterranean is getting dry in terms of drought, but it's not the same thing. Okay, it's not necessarily just precipitation. But anyway, in some countries, especially for instance, Northern Europe or whatever, we are pretty sure that this is an effect of human-induced climate change. Now, what about the future? Well, for the future, we have our tools, which are this one. No, not really this one. Well, what can we do? Well, the projections for the future start with what we call ensemble of opportunities. Basically, what we think that human will emit in terms of greenhouse gases. We don't have the crystal ball, so we don't know what will happen, but there are people that their job is to make assumptions. Okay, assumptions are based on, for instance, the projection of GDP or socio-economics and economy, or many assumptions. And based on this assumption, they come out with emission of greenhouse gases. And they go from very high emission, like this one, to very low emission. And actually emission then actually decrease instead of growing up. And these are the ones that actually are compatible with the Paris Agreement, 1.5 degree warming at the length on the long term. So then we use these projections, these assumptions, into climate model, and we see what the climate will look like with these assumptions. And we have this kind of results. So this is basically the table. You have the mean temperature compared to pre-industrial at different time slots in the near future, the mid future, and the far future, according to this socio-economic scenario of emissions. And this is the same, just in a graphical way. The important message here is to understand that in the next, let's say, 20 years, 30 years, the temperature increase won't depend on the emission scenario. We are committed to this change regardless what we do. The problem is that on the long term, the scenario will make a huge difference. There's a huge difference between a very high emission scenario compared to a very low emission scenario in terms of 2-3 degree warming. Okay, but for the next 20, 30 years, we will be there regardless of the emission scenario. Now, let's go back to this picture, which now I think you know everything. You can understand everything about this picture. But what's important is that this picture was redrawn with more recent data. And when you do that with most recent data, you have this kind of picture. So the blue curve is the temperature measured in Switzerland between 1864 and 1990s. And the red picture, the red curve is the measured, actually the PDF, the probability of having temperature between 1991 and 2018. And if you see, they are very different. not only in the mean, you see that the mean in the 60 whatever was around 14.2, now is around 16 degrees, so 1.7 degree warmer. But there is a bigger problem. So this is one. What was considered normal in the 70s, whatever, in the 80s, so something that happened once every 2 years because this was the normal climate here. Now, the probability of that climate is very low. So the climate that was normal in the 60s now is considered a cold climate, a cold extreme. Not only that, but we have that what was considered extremes in the 80s, now we have many more of these events recorded. This actually happened. So many more extremes, many more events that in the 60s were considered extremes. They have happened in today's climate. But even worse than that, now they have events that never happened in the previous climate. These are new extremes. Okay? So it's like playing dice, but the problem is that when you play dice with loaded dice, assume that you have, instead of having 2 normal dice, where the probability of having, for instance, 12 is 1/12. One of the dice, instead of going between 1 and 6, going from 2 to 7. So you actually increase the probability to have the tail of this distribution. You have higher probability of having 12, but you still can even have a small probability of having 13. That could never happen if you play with normal dice. Okay, this is also a picture from the IPCC. This is a kind of projection of what can happen or what is projected to happen according to 3 future, one in 1.5 degree future, 2 degree future, and 4 degree future. And the reference is a 1 in 10 years event. This is extreme heat event. And of course, the same, the pre-industrial, this event happened once every 10 years. But if you see in a 1 degree world that's actually now, this event happened already 3 times in 10 years. In a 1.5 degree, they happen 4.5 times. In a 2 degree, they will happen 5 times out of 10. It means once every 2 years. And in a 4 degree, actually 9 times out of 10. And also the intensity of this event will increase drastically with the global warming. This is not a linear increase, it's the point. Even for 1 in a 50 years event, which happened 1 in 50 years in the pre-industrial, now you see that the increase is not linear. In a 4 degree warming, it actually again happens nearly every year. The same for precipitation events. This is a more complex picture. I don't want to explain it into details, but the meaning of this picture is that that we call it climate impact drivers, which is a word that I don't like. Call it hazard. Okay, impact of changing climate, hazard, like extreme rain, extreme precipitation, extreme cold, extreme wind, this kind of events. Well, the problem is that in the future, we'll have this kind of hazard happening at the same time in different locations. And if you, this picture says that in a 2 degree world, all region will have at least 5 of these hazards happening at the same time. And nearly all region will have 10 of these hazards happening at the same time. It's not just temperature, everything will change. Okay, now let's have a look to more direct impact of climate change, not just temperature, not just precipitation, but something that actually is probably more visible for the people, but also will have an impact, for instance, on economy. Okay, so this is a result from a project that we have done at the JRC. It's called PESETA, which is basically economic assessment of the impact of climate change over Europe, which is the 4th iteration. So we started with the projected change in temperature and precipitation over Europe in a 1.5 degree, world, in a 2 degree world. So these are the, let's say, Paris Agreement world. And then we consider a 3 degree warming world, which actually is a world without mitigation, okay? And then we applied a lot of impact models and to study the impacts, for instance, on forestry, on biodiversity, on energy production, agriculture, infrastructure, floods, river floods, coastal floods, forest fires, heat and cold extreme events, and blah, blah, blah. And then, well, we studied the economic impacts of that. So I don't want to enter into details, but for each of these impacts, they have the change in, for instance, let's say this is extreme heat, okay? So they calculated the number of people that annually are exposed to a 50 years heat wave, for instance, so a very strong heat wave. So these are millions of people. So let's say in today climate, we have around 9.6 million people. But in 1.5 degree, this is 10 times more, 103 million people, up to 200 whatever people in a 3 degree warming. And this is the number of calculation of people that actually been killed by this heat. So we have around, this is yearly, I guess. So again, you see that it's more than a 30 years fall between the base climate and the 3 degree warming climate. They do the same for other hazards like the water scarcity. So this is number of people living in water scarcity condition between the base climate and the 1.5 degree and 3 degree warming climate. This is drought, and they also calculate the loss in GDP, percentage of GDP compared to the, so C is double actually between the base climate and the 3 degree climate, and the windstorm. Windstorm does a change just because actually model, there's a problem. It's not a problem, but it's because the wind and model don't change very much, but that's not the big problem now. Oh, let me go back if I can. Yes. So the message of this is that mitigation, mitigation means basically emission reduction, okay? Policy to emit, to reduce the emissions is a way to avoid something that we will not be able to manage. We will not be able to manage a 3 degree warming world even. So we have to try to avoid that. So to stay well below that. So the other side of the coin is called the adaptation. So we have to adapt or to manage to the condition where we cannot avoid. And for floods, basically the coastal floods and the river flood, they actually did that. They studied some adaptation measures, for instance, dikes, the height of the dikes, or even water reservoirs, and they calculate the change in the damage of the people exposed to damage if we had adaptation option or not, both in a, let's say, in a climate with or without adaptation. And again, the change is staggering. Is 10 times less, for instance, for coastal floods. Or there is yes, it's at least a twofold increase for river floods. So again, adaptation is a key. We cannot live in a world that actually changes without adapting. Now, this is a sort of summary of this project. Basically, this is the change in GDP, so the loss, for 5 climate, let's say, called hazards, so heat, agriculture, energy production, drought, and infrastructure, I think. But this, what you have to understand from this picture is that it's very uneven in Europe, okay? Not everywhere will have the same problems, but especially on the Mediterranean, the impact will be very, very, very large. And not all sectors will actually have the same impact. For instance, agriculture in the northern countries will actually benefit from an increase in temperature. But the cost of the total, if you calculate the total damage will always be negative. And this is the impact of, I think, in billion euro, I think it is yearly, in a 1.5 degree, a 3-degree warming world when you consider all the hazards. And this is without considering mortality from heat waves, for instance. Now, the European Commission has just published what they call the cohesion report, a report on economic, social, and territorial cohesion. And this is a picture from us, from the Jersey. And again, this is more or less the same picture as before. This is the number of the cost, the additional cost to the economy of today. When you consider the impacts on 5 sectors, basically flood, drought, windstorms, labor productivity, energy demand, and transport. And this, the second picture is this one, is the human exposure to harmful climate, so the impact of this. And this is the number of people, actually the mortality to extreme climate, can be either cold or hot, actually. And again, what is important to understand is that this is why the DG ECO, which actually is the one responsible for the cohesion policy in Europe, is very interesting. This because we have to understand there are huge differences between Spain, for instance, or Southern Europe and Northern Europe. Okay, so if you lived in Italy in the 80s, probably you will remember this picture. This picture was taken from an advert for, actually was a toothpaste. Was, of course, I cannot say which one, but the message was to prevent is better than to cure, which when we can translate something like better than safe than sorry. So, okay, this is the point. We have to do everything we can in order to prevent the worst consequences of climate change. And for those we cannot avoid, we have to adapt. Okay, now I will end up with, again, these are, as I said, personal reflection that I told students when I was in actually my former high school, talking to the students 30 years after I was there. So it was weird for me to be there, but it was very nice. So the first thing I say is that the climate change is a global problem. It will affect everybody. The problem is that it will affect people differently depending where they live. And the most affected people are those living in the poorest country. And it's not just a matter of, it's not really their problem, if you really want to be bold. I mean, consider just sea level rise, for instance, okay? We know that there are people living in places where sea level rise will actually eat their land. And their people have to move somewhere else. Also, there will be places where temperature will be unbearable to live or to harvest or to have livestock. So these people have to move. They will move somewhere. So these are one of the consequences of climate change. They will be called, or actually already called, climate. I don't remember the word. But actually, these people need to be moved somewhere else. But anyway, there is a huge ethical problem. Okay. So it is a huge economic problem, and this is one of the biggest issue why tackling climate change is complex, because we have to go from an economy based on carbon to an economy which in the end has to be completely decarbonized if we want to keep the 2-degree warming target or even the 1.5-degree target. We have to reach net zero emission. This is clear. There is no other way. How to do that? Well, of course, policy can make a huge impact. for instance. You will probably know about the European Green Deal, okay? I don't want to talk about that. I think there will be someone from, actually my colleague from the Commission talking about that. But this is what the policy can do. For instance, the reason why you cannot buy this kind of bulbs anymore is because there was a law that said, well, from one day, this kind of bulbs cannot be bought anymore. You have to buy this one. They are much more efficient. So this is very easy. It's very effective, and it's a beneficial win-win solution because they are more or less the same. Well, probably a bit more expensive, but actually they are much more efficient. So actually you save electricity, they are good, and so on. The problem is that some other policy that we know that are essential are much or less popular, okay? But some, there is no other way. We have to deal with that problem. So technology can help. Yes, of course, technology can help. We can build wind turbines, we can build solar plants, we can build electric cars. But we cannot live with the assumption that this is the solution. And I make you a specific example. You probably have heard about carbon sequestration, which actually is a way to suck the CO2 from the atmosphere. This technically, it is possible. And chemically, it is very simple, as far as I understand. And this here is the first commercial CO2 sequestration factory. This was built in Switzerland, I think in 2017, if I remember. The problem is that this factory absorbs something like 900 tons of CO2 per year. And this is the equivalent of 200 cars. The global emission in 2018 was 37 billion tons. So if you want to capture, for instance, 1% of the 2018 emissions with this kind of technology, we will need something like 400,000 of these plants. So this clearly is not a solution. We cannot just bury our head in the sun and say, oh, technology will solve the problem. No, it won't. It is an ethical problem. It is an ethical problem because, as I said, we are living in a rich world. We won't really care. We live with our cars, with our electricity, with our swimming pools. The problem is there are millions, billions of people that live in countries where conditions are much different. And it's not only that. You have to realize that when the Paris Agreement were discussed, and in the end it was approved, India was very much against that. And what they said was, well, look, there are millions, hundreds of millions of people in India who live because of electricity, which is created with carbon factories, okay, carbon plants. We cannot simply tell developing countries to stop emitting, stop burning carbon when it's coal, okay? Because they can't. We have to find a solution. And also it's very hypocritical from us, rich country, to tell China, for instance, to tell India, which they have a per capita CO2 emission much lower than ours. We cannot simply tell them, oh, you have to stop emitting, and we can go on as nothing happened. So the good thing is everybody can do its little share. The problem is that we have to realize that. We have to realize that we cannot pretend to live with 25 degrees in winter in our house just because we don't want to wear a jumper. Or we have to realize that we cannot live in a world where I drive my car to do 100 meters because it's raining. Or I can keep the light on all day just because I want it, okay? It's very simple. It's again, it's win-win situation because in the end, if I switch off my lights, if I turn down my heater, actually at the end, I will spend less money, so I'll be happy. But we need to change mentality. And I remember when I was very young that in Italy we introduced the recycling for the rubbish. So we started dividing, for instance, glass from paper, from waste. And now I can't really put the glass, or it's really hard for me when I go in places where this is not done, to put the glass in the waste, in the so general waste. To me, is unnatural. So we have to train the new generation. So this is important to talk to students to do this, to learn this, because when it's become natural, they will do it, because for them it will be natural to do that. This is another example. This is a picture that I could have taken. This is not my picture, but I was there. This is Cape Town in 2018. I think it's February 2018. And Cape Town in South Africa, you may have heard of the problem. Between 2017 and 2018, they had a multi-year drought. And Cape Town was the first big, let's say, metropolis which actually risked to end up without water. And this was a real problem, a real issue. At the point that they was actually thinking to go to the South Pole, get an iceberg and draw it to South Africa to get water. There was actually, there was study that for the feasibility of that. The people you see in the picture is people queuing for water in the fountains. But when I was there were posters like that. Basically, they say, well, we have 50 liters of water every day. And you say, okay, 50 liters is not little, 50 liters is quite a lot. But then if you think that when every time you flush the toilet, that's 10 liters of water. So basically, you couldn't flush the toilet unless it was very, very, very essential. You couldn't, of course, water your garden. You couldn't, of course, fill up your swimming pool. You have a timer in your shower. You said, well, you have 3 minutes, even 2 minutes of actually running water. Not only that, but you had to collect the water while the water was getting warmer. It was actually recycled. It was a very, very learning experience. And the message here is that we cannot afford to waste resources. Resources are limited, and we don't realize that. We waste a lot of water, food, electricity, just because we think that we have it, so why not? But when you face a situation when these resources are actually ending, then you think twice about that. And again, it's very, very nice experience, or not nice, but learning experience. So I end up with the first suggested readings, if you want to understand a little bit more. First one is the summary for policymaker for the IPCC 1, which contains all the technicalities I told you in more or less a language that the policymaker can understand. So you should be able to read it without any problem. But there is actually a better report, which was written in collaboration with the Actuary Association, which is this one. And this actually is really, really, really well written. So if you want one, let's say, book, it's not a book, it's a report to read about the finding of the IPCC report, read this one. This is actually excellent. Then if you want to go a little bit more into details about the impacts of the climate change over Europe, there is the report of the PESETA project, which is available, and also the report of the, this is by the Environment Agency, which has just published the European Climate Risk Assessment, is more or less an extension of the PESETA report. And also I end up with, this is the cohesion report. But then I just discovered a report, which I just read, but I think for you, it's actually as a teaching community is very, very important, which is this one. It's called Choosing Our Future. It's a report from, I don't know exactly who, but it's about education. And they have a lot of nice statistics. They are statistics from, I think, 8 countries, developing countries, and about how climate information is actually thought there, but also the impacts or how these pupils, actually, they are very young, think about environmental problems. I think this can be a nice reading for you as a community. Now, I end up with this. Okay, this is a picture. You won't see anything, but this is actually part of it, part of its charm. This is not the original picture. The original picture was actually even worse, was much worse quality. This is a remastering one. So this was a picture taken in 1990, okay, by NASA. Okay, so what are we looking at? This is the picture taken by the Voyager on 14th of February 1990, and this is the picture of the Earth. Okay, the first picture of the Earth taken from deep space, from 6 billion kilometers, and this is us. The little dot there in the light is the Earth. And actually, the light is not a beam of light; it's actually a reflection. Showing that, but this is actually a very nice picture. And Carl Sagan, who was an astrophysicist, but was one of the best science communicator, took this picture and wrote a sentence about that. He called it the pale blue dot and wrote this. If you look at that, you see a dot that's here, that's home, that's ours. And on it, everyone you ever heard of, every human being who ever lived out their lives. Every hero and coward, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species live there on a most of dust suspended in a sunbeam. Our planet is a lonely speck in the great enveloping cosmic dark. To me, this image underscores our responsibility to deal more kindly and compassionately with one another, and to preserve and cherish that pale blue dot, the only home we haven't known. And I end up here. Thank you.
So, great. Thank you very much for this very rich presentation, and also for making technical and complicated concepts much easier to grasp and understand. I would say you have given us a lot of details, but also on the physical basis of global warming, but also some deep insights into the big picture of global warming. So from a social, an economic, and an ethical point of view. I'm pretty sure that we all have some questions or thoughts that we would like to share. And I will now hand over to our GRACE project manager, to Daniela Ferrari, to chair the Q&A session. And again, thank you so much.
Thank you, Dr. Dosio, also on my part for this insightful and engaging presentation, and also for the last image that you gave us, very touching. So as Tiziana says, we now have some time for questions. If you'd like to ask a question, you can either use the chat or you can raise your hand. And if you do so, please switch on your camera. That would be nice. Please, if you can, we only have 15 minutes left, or even less, for a question, so keep them brief so that we can cover as many as we can. Okay, so we have a question from Gabriele Calta. Maybe I will read it to you. How much is the heat human activities directly emit compared to the one due to a greater concentration of CO2? Industries, transport and traveling, the internet, heating, conditioning houses during winter, summer, operating over, and our living and consuming causes a direct amount of heat go into the atmosphere. Is it negligible, or has it to be taken into account too?
I have to read it again because it's very long. How much is the heat human activities directly emit. Okay, you can calculate, if this is the question, okay, you can direct calculate the fraction of temperature increase that is directly due to human activities, if this is the question. I don't have the picture, but you can find it easily in the IPCC summary for policymakers. There is a plot, there is a picture when all the components are shown, and the warming, I think, is around, I think, a 0.8, if I remember by chance. This is the human-induced climate, the contribution of human-induced CO2. And then, of course, you can also split it in the different activities, but then becomes quite complicated.
Okay, there is another question from Mr. Duquesne. What could we answer to people who claim that if everyone does, I guess, his share, then we can cope with climate change?
Well, okay, to me, what I would say is two things. The first, there is a problem. We know there is a problem. Okay, this must be very clear. We cannot avoid the problem. To solve the problem, it's complex because it's not just a problem that we can solve by ourselves. There must be a huge change in let's call it our lifestyle. It doesn't mean that we have to go back to the candle, okay? But something has to change. And this kind of radical change has to be taken by policy, because the policy is the only meaning we have to impose some changes. But then there is something we can do. And again, as I said, these are small things that will help. And basically, why not? I mean, this is, again, as I said, is a win-win solution. And at the end, if I put double glasses in my house, at the end, I will consume less. I will be happy because it will cost less. I will use less heating. I don't see why people is complaining about this kind of solutions, because in the end, they will be actually benefit, economic benefit on a longer term. And this is something that to me is not yet permeated in the let's say general layman. And this is also a problem, if you want, of communication, and something that we probably start to realize a bit too late. Then we as, let's say, science, but also the policymaker, should communicate in terms of benefit of change, of mitigation, instead of, oh, we have to do that because otherwise we all die, because that's not true. But we have to say, well, there is a huge opportunity there to be used. And if we do that, there will be a concrete advantage, even in terms of economics. So this can be a strong message.
There is another question about the ethical dilemma, the so-called 2080 ethical dilemma, the fact that 20% of the population has 80% of their resources. So, and is responsible for the most amount of emissions. We can do individually what we can, but then the very rich people emit so much and use so much resources.
Yeah, but again, this is a very general question. But the only thing that we can do is, now I talk in terms of, let's say, European Union, we can set up the example. I know people that say, well, what's the point, since the US, for instance, or China will emit much more than us. But if we don't do it, I mean, there is no reason why we shouldn't do it anyway. And again, if we set the example and emissions are reducing, as in a way, we are reducing less than the 90s, that's clear, especially at the European Union level. If we set the example, if we convince other countries that there is a possibility to prosper, even from the economic point of view, even with the energy revolution, call it as you want. If we set the example, people will follow us, because at the end, it will be economically much better. Especially the cost of mitigation is much. I mean, the economic benefit of mitigation will be much higher than the consequences if we don't do that.
Okay. So Christina Vanke is asking, maybe she missed something, but she did not understand why a cleaner sky over Europe causes higher temperatures.
Well, because there are less clouds. If there is no clouds, much solar radiation comes on the land, so it's hotter.
An interesting question from Alexander Palman.
Yeah.
Do you prefer the expression global warming or climate change?
In my opinion, I use them as a sign. I change them. I don't really matter. I know there is a technical differences, and because the technical difference is that climate change is more than temperature. Because a change in precipitation pattern is not just global warming. But I think that everybody will understand if you tell global warming and you mean climate change. So technically they are different, but I don't think that's a real problem. If you really want, we are living in a global warming phase, but we will definitely live in a climate change phase where not only temperature will change, also precipitation. And the problem with precipitation is that it will be much more extreme. I mean, the problem is that we will have probably less total precipitation. It will rain less, but when it rains, it will be much harder. So the pattern of precipitation will change. So in this meaning, also precipitation change, so that climate change, not only warming, not only temperature, but the two are related, of course.
Okay, maybe we have time for two more questions.
Yep.
Laura Tamina is asking about distribution of heat in the ocean. So in what ways does climate change affect ocean circulation and the distribution of ocean heat?
Yeah.
And how will this process influence Europe?
Yeah. Okay, you have to understand that ocean storage an enormous amount of heat. And also not that, but it releases much later than land. This is why when you are at the sea, you have the sea breeze, because the sea breeze is the difference between the temperature on the ocean and the temperature on land. Land becomes hot very quickly and then becomes cold very quickly. The ocean store the heat much longer. This is a consequence, is that we are still pumping heat into the ocean. The ocean is absorbing this heat and it will releases much later in terms of decades. So even this is one of the reasons why even if we stop emitting today, will have consequence for the next 30, 40 years, whatever. This is one of the problems. The other problem is that there's a problem of salinity. For instance, if you think about the pole, which is actually ice, so if the ice melt, this kind of water will enter into the ocean. We have different salinity, so it means that it can actually change the circulation. This is one of the big questions about the so-called Atlantic AMOC, what the circulation, the bigger circulation in the Atlantic Ocean, actually the one that keeps actually the UK warm. If this changes or this actually stops, that would be a huge change in the climate. But we don't know yet if this will happen, when this will happen, and how. There are studies that say it can happen sooner than expected. Some say, well, it's not really clear. But this is one of the problems, yes. And also the other problem is that, of course, when the water heats, actually becomes more less dense, wind becomes less dense, and actually becomes bigger. This is why the sea actually rises. Okay, and this also is a problem. Now it's not much at the moment, but it's still increasing. And this is something, again, that we can't stop for the next 20, 30, 40, maybe even 100 years. And this will have consequences overall the cost of the low land countries, but even in Europe, for instance.
Mhm. So maybe we could just finish with those two questions. Again, Mr. Ducan was asking about the importance of tipping points for understanding the consequences of climate change, while Raul Pinto was talking about what do we do when people don't take care of resources. And he gives the example of LED lights, that they consume less, but then the cities are filled with LED panels.
Yeah, well, okay. Tipping points already says something. One of the tipping points is this, the ocean circulation. The other tipping point is the nitrogen in the permafrost. There are others. It's not clear yet what will happen, but there are a lot of people that are actually starting studying them in terms of probability to happen and also consequences. And I think the next IPCC, the 7th cycle, will actually look into this more into detail. The short question, the short answer is that it will be a disaster if some of this actually happened. Regarding resources, well, what to say? Again, it's a matter, we have to change mentality, and you have the opportunity to teach students to change mentality. And to me, the most important thing is to make them understand not to waste. And again, to me is astonishing. Then we can buy stuff that actually costs so few, so little. And this to me is not sustainable. And this is not the real price of the stuff. And with the consequence that if it's cheaper to buy something and throw it away rather than, for instance, repair it, there is something wrong in the system, in my opinion, and this is my personal opinion. But something has to change. We cannot afford it.
Thank you, Dr. Dosio. Thank you, all of you, for joining us today. A special thanks, of course, to our speaker for such an informative and insightful session. And thank you to all of you for your active participation. We hope you found the discussion valuable, and we hope to see you in future webinars. If I may, I would like to kindly ask you to take a moment to complete a brief satisfactory survey about this webinar. The link is in the chat, and it will take less than a minute to fill in. We would be very grateful because this will help us improve our future sessions. So as a reminder, I would like to tell you that if you miss any part of this webinar, it has been recorded, so we can send you the recording very shortly. And one more piece of information, Tiziana and I will stay on a little bit longer. If you have any questions about the webinar series or the residential course, we will be happy to give you further information and further details. So feel free to stay on, to stay connected. Otherwise, thank you again. And Dr. Dosio, we're very grateful for your time and for your expertise.
Yeah.
That was a pleasure. Thank you.
Yeah, thank you also on my part, actually. I think we had a very good start to our series, and our next webinar will be exactly on justice and climate. So it will be an opportunity to delve into these ethical and political issues and questions you have already raised for us today. So really, thank you for being with us today. And
Bye-bye then.
bye, and thank you.
Thank you. Thank you very much. Thank you.